Welcome back. In this lesson, we're going to talk about chemical equilibrium. Reactions are always reversible. It may not seem that way because sometimes it's very easy to go one direction and very difficult to go the other. But in reality, a reaction has the option, let's say we have A plus B going to C. Well, the C could also then break apart and make A plus B, which might form another C, back and forth. And so we combine those as a reversible reaction. A plus B makes C reversibly, and we usually write those with sort of a double arrow. When I'm writing them, I write them kind of more like the blue, but typing is a little bit of a challenge with Microsoft products, so we've got the double arrow there. Now we define the equilibrium constant as K sub EQ. It's going to vary with temperature, so it's a function of temperature. And it's the repeated product of the mole fractions to the stoichiometric coefficient power of all the products in the numerator and all the reactants in the denominator. Pi, if you haven't seen that before or haven't seen it in a long time, is a lot like capital sigma. Capital sigma is a repeated sum of all the different terms. Pi, being a Greek letter P, is a repeated product. Now, you may, when you take an equation like this and try and solve it, end up with different numerical solutions. However, all the answers for x must be numbers between 0 and 1 because they need to be physically possible. This will make more sense when you see an example. So let's look at an example. Now in this particular case, A, B, C, and D are actual chemicals, but I don't want to write all those all the time. So we've just simplified it as A plus B reversibly forms C plus D. In this particular case, the equilibrium constant is 4.87. And we want to find the extent of reaction if there's a feed of 1 kilomole that's equimolar A plus B. So what I've got going on is I've got my little reactor here. Okay, I have 1 kilomole, 0.5 kilomoles A, 0.5 kilomoles B. And coming out of this is going to be A, B, C, and D. I just don't know the proportions of those yet. Okay, so I can do a basis, and so I'm going to define this as my basis. I can do a material balance table. So I have the feed and the product. Okay, on my feed I have 0.5 kilomoles of A, 0.5 kilomoles of B, 0 kilomoles of C, and 0 kilomoles of D, making a total of 1 kilomole of this. And all of these are in kilomoles. So these are mole fractions up here. This is kilomoles down here. Now I don't know what's going to come out. So I have XA, XB, XC, and XD, and a total of F2, right? Or product or something like that. But logically, can we figure out what the flow rate is coming out? Well, I have 2 molecules on this side of the reaction. I have 2 on this side. So I will never have a change in number of moles. They will just simply turn into different things, right? So I actually do know that the flow rate coming out is also going to be 1 kilomole because it is equimolar, the reaction is. The number of moles at the beginning is equal to the number of moles at the end. So I know that. So I have these 4 compositions that I need to determine. Okay, so I'm not really going to treat this like a normal process because what we're trying to do here is work on the equilibrium constant. So for the equilibrium constant, the value is 4.87.